Hello, everyone, and welcome to our presentation as part of the MIT in Big Data Science course. We are Group 11, and today we're going to delve into the fascinating world of AI and machine learning, specifically their application in wildlife conservation. Our project focuses on creating a crocodile identification system, a tool that could revolutionize how we monitor and protect these incredible creatures. Let's dive in. Our project is divided into two main phases. In phase one, we focus on crocodile identification. This involves training a model to recognize and identify crocodiles in images. Phase two, on the other hand, is about crocodile re-identification. Here, our aim was to distinguish between individual crocodiles. And let me just say, this task presents its own unique set of challenges. We formulated the following objectives for our research project. We employed CNN methods to identify crocodiles within drone-derived imagery that could be used for basic population surveying, such as counting individuals. Next, we investigated the feasibility of applying instance-level analysis that would enable individual recognition of the crocodiles based on pose estimation methods and enable implementation of methods such as mark recapture as a method of population modeling. Then we aimed to integrate our developed solution into the existing workflow to automate and optimize the population modeling process from image acquisition all the way till population estimation. The backbone of any AI project is data. For our project, we used a dataset of 7,870 images, each with a resolution of 4,056 by 3,040. The total data size was 29.7 gigs, with an average image size of 7 megabytes. The data also consisted of 1 hour and 7 minutes of video footage of the same crocodiles, with a total of 4,029 frames extracted from the 77 videos. A summary of the photographs features are presented in Table 2. These images were recorded on various dates and times, providing us with a diverse set of data to work with. This diversity is crucial as it allows our model to learn from a wide range of scenarios. As I said before, we split our project into two phases, with phase one focusing on crocodile identification and phase two focusing on crocodile re-identification. We formulated the following objectives for phase one. We aimed to develop a model with the ability to detect crocodiles within an image and develop a model robust enough for applications beyond the context of the training data that we had created. And we aimed to deploy the model for real-world application and visualize the results of the output model. In phase one, we started with image annotation. This process involved labeling the images to identify the crocodiles. We then trained the YOLO V8 model using these annotated images. Training a model is like teaching it to understand and interpret the data. Finally, we tested the model to see how well it had learned from the training process. For image annotation, we used a tool called RoboFlow. This tool allowed us to label and categorize our images effectively, which was a critical step in training our model. Image annotation is like providing a guide for the model, helping it understand what to look for in the images. Once our images were annotated, we trained our YOLO V8 model on 92 of these images. We used various hyperparameters such as a learning rate of 0.01, a mini batch size of 16, and 25 epochs. This process helped our model learn and understand how to identify crocodiles. We used something called mean average precision, or MAP, to evaluate our initial results. This is a common method used for object detection tasks such as ourselves. MAP is calculated based on something called intersection over union, or IOU. Now, think of IOU as a way to measure how much our model's predictions overlap with the actual truth. So it's like a score of how well our model did in predicting the exact location of crocodiles within our images. Our initial map score was 0.956 when we used an IOU of 0.5, and it was 0.768 when we used an IOU between 0.5 and 0.95. Now, these numbers might seem a bit abstract, but what they tell us is that our model did a pretty good job at accurately locating the crocodiles. However, when we look at the map score of the IOU ranging from zero point 0.5 to 0.95, we see that it's lower. This tells us that our model is robust, but as always, there's always room for improvement. We also noticed that our map score reached its highest point at around 20 epochs. So an epoch is a complete pass through the entire training data set. So after about 20 rounds of learning from the data, our model's performance plateaued. And that tells us that we can actually stop the training, or we could limit our training to 20 epochs just to save on processing time and power and resources. Looking at our training and validation loss results, it seems like our model was learning well and not overfitting. So, overfitting is like studying too hard for a test. You might do well on the practice questions, but struggle to apply what you've learned to new problems. Luckily, our model didn't have this issue. So, after we trained our model, we wanted to see how well it was doing. We looked at three things: the true positive rate, the true negative rate, and the false positive rate. These are just fancy terms for how often our model was right, how often it was wrong, and how often it got things mixed up. We used a test set of images that the model hadn't seen before, but that were similar to the ones that we had trained on. For example, the pictures were taken at the same time of day as those in the training data set. This was to see how well our model could apply what it learned to new but similar situations. The results were pretty promising, but it's clear we still have some work to do. Our model did well, but we think with a bit more training, it can do even better. For our second test set, we decided to shake things up a bit. We used images that were quite different from the ones we used for training. Some of these images had buildings in them, and some didn't even have crocodiles at all. We wanted to see how well our model could handle these new situations. Just like with our first dataset, the results were promising, but we realized that if we want our model to get better at dealing with images that have buildings or no crocodiles, we need to include more of these types of images in our training set. It's like the old saying goes, practice makes perfect. Finally, we decided to really put our model to the test. We used a completely different data set with pictures of crocodiles taken by a drone in India. We wanted to see if our model could step out of its comfort zone and still accurately identify crocodiles in a completely new environment. But just like in any good story, we hit a bit of a plot twist. Our model struggled with this new challenge. It was still able to correctly identify crocodiles, but it also started seeing crocodiles where there were only rocks. This tells us that if we want our model to be useful in different real-world scenarios, we need to give it more diverse training experience. It's like training for a marathon, but only running in the park. And then being surprised when we struggle with the hilly parts of the race. We need to include more variety in our training data to prepare our model for all the different situations it might encounter. So from the results in phase one, it's clear that we still need to train our models on more images and also take into account the diversity within these images. But also we could investigate how the feature extraction is being carried out by the model. That way we can optimize our images to make sure that the model only extracts our desired features. And that is what we will do going forward in improving phase one of our project. But I will hand over to my colleague, Lisejo Matojane, to explain phase two of our project.
In phase two of our project, we have three main objectives. First, we aim to develop a model with the ability to re-identify crocodiles from images. Second, we plan to compile a database of individual crocodiles. And third, we aim to enable tracking of these individuals. The most significant challenge to achieve the re-identification task of these crocodiles is that high-quality imagery is required for instance-level identification. The crocodile's unique patterns, scales, etc. needs to be visible in our training data, and sufficient training data is also required. This was achieved in a study that we've referenced called the Mugger study. But we feel as though this report merely proved that it was theoretically possible to use CNNs to do crocodile identification, but they didn't really prove that it would be practical. Our study aims to develop a framework where low-cost drones could be used to recognize crocodiles with lower resolution imagery. In our figure, I show as an example pipeline of this process, whereby a new crocodile is identified in the wild. It's compared to our database of known crocodiles, and if it is deemed to be new, it is added to the database. In this slide, we delve deeper into the concept of key pose estimation and its application in our study. Key pose estimation is a technique used in computer vision that involves predicting the position of key points or joints on an object or a subject. In the context of human pose estimation, these key points might be parts of the body, such as elbows, knees, or the tips of the fingers. However, in our study, we apply this technique to crocodiles. We identify and predict the position of key points on a crocodile's body, such as the snout, forelegs, upper torso, lower torso, and hind legs. The purpose of this is to create a unique pose for each crocodile based on these key points. This pose can then be used to re-identify crocodiles in different images or over time. By applying key point pose estimation to crocodiles, we aim to develop a model that can accurately and consistently identify individual crocodiles, which could have significant implications for wildlife monitoring and conservation efforts. The key idea is that this avoids the issue of requiring high quality imagery where the individual scales and features on a crocodile surface are required when training CNNs. We circumvent that issue entirely. To achieve pose estimation for our study, we adopted the SLEEP framework, which is an open source, deep learning based framework for multi animal pose estimation and tracking. The first step in the process is pose annotation, for which we are using the SLEEP framework GUI. This image shows how we use SLEEP to annotate key points on the crocodile's body, such as the legs, the torso, and the snout, etc. Once we have labeled and annotated our training images, we move on to training our sleep model. We use an Atom optimizer with AMS grad, a learning rate of 0.01 with a batch size of 4 and early stopping at 200 epochs. The input size is 1280 by 720, and we use the mean square error as our loss function. Model architecture is based on a pre-trained UNet encoder, and we have at least 60 images for training. Depicted is the percentile distribution of the localization error. It shows how off the model was from the ground truth of the key pause points. Another way to summarize this is through precision recall curves shown in Figure 6, which evaluate how well the model does at different thresholds of OKS scores. The higher the threshold, the more stringent are our criteria for classifying a prediction as correct. OKS scores known as Object Key Point Similarity, or OKS, measure the similarity between the predicted key points from our model and the actual key points from our data set. To summarize the model accuracy, we take the average of all these thresholds to compute the mean average precision and the mean average recall. For this, we got an MAP of 0.34 and an MAR of 0.42. In conclusion, our findings suggest that the approach remains viable and promising. Being able to identify crocodiles by their physical attributes, such as limb lengths and limb positioning, is highly advantageous, as opposed to attempting to recognize crocodiles by their actual patterns on their skin, which requires high-resolution imagery and high-end drones which are not easily accessible. The sleep model requires at least 1,000 labels to reach an MAP of around 80%, as shown in Figure 7. This image was taken from the sleep published journal. Currently, our training labels sit around less than 100, with each labeling task taking around an average of 6 minutes. Therefore, we need to increase the number and diversity of our training data and labels to get to an accuracy around 80%.
Finally, we integrated all these components to create our crocodile identification system. This system represents a significant step forward in wildlife monitoring and conservation efforts. By accurately identifying and re-identifying individual crocodiles, we can gain a better understanding of their behaviors, movements, and population dynamics.